waveguides, basically. It's not really a sexy topic of photon entanglement or quantum computing, but what we're going to cover today is essential for when you're trying to specify a processing system for waveguides. So there's certain features and types of operations you should be looking for, again, when you're looking at purchasing some type of processing equipment. Loading is important. The better loading, more repeatable loading, more repeatable results. Fixture alignment and calibration, this is what's going to determine the end face geometry of the edges of your chip. Polishing and process control, this determines the amount of material removal, which is important with waveguides, and also the final surface finish of the component for optical coupling purposes. And finally, any type of equipment you specify, it should have a pathway from an R&D function to a production function. So R&D, we're talking for like maximum flexibility for process development. In production, we're going to look for high throughput as much as possible. One thing we noticed is that the dicing of waveguides is very inconsistent. We see initial damage, chipping on the order of several hundred microns possibly. And before you can even consider polishing this waveguide, you basically have to get rid of all those defects, and you have to co-planarize those surfaces before you move to the next finer polishing steps. We've also seen epoxy deposition on waveguide edges used to protect the actual waveguides. And again, you have to have process development that remove this epoxy co-planarization. And ideally, you need a chip, a waveguide chip, that has a datum point that can be used for repeatable loading purposes also. When you're in the R&D phase and development phase of the PICs, dimensions and angle geometries are not already determined. So there's all these changes in widths of chips, and any type of holding mechanism has to accommodate different size the clamping mechanism. And additionally, the clamping mechanism should be such that it keeps the chip flat against the mounting surfaces, the mounting surface, and that the chip does not lift off during the process when you change all your end face geometries. Additionally, most waveguides have very sensitive areas that you should avoid contact with when you're designing a clamping mechanism. Some circumstances you can't avoid it, and if you can't avoid it due to dimensional restraints, you need to use clamping devices that are softer, some types of plastic, or in some cases, placing protective liners over the fixture itself to avoid damage to the chip. Any polishing machine should have referencing positions. This would be for loading the chip on a repeatable basis. So the fixture should lower down to the polishing surface and provide a means of repeatable loading with the same protrusion of the chip. And this is important when you're going from chip to chip or one technician to another technician using the machine itself. So there's no subjectivity in the loading process. In this example here, this is kind of a standard size chip, maybe 10 millimeters in width. Loading on the machine is fairly simple. However, we've seen smaller waveguides, and when you get to a certain point in size, loading on the machine is not ergonomic. So you may want to consider offline loading using some type of a carrier device where you load the chip offline, and then you take that carrier and place it on the polishing fixture itself. And you may need video assistance for some type of loading. I mean, to get very precise and exact in referencing, this will help also. The fixture alignment, again, just like in development, the PIC dimensions can change, so can the end face geometries. Some end faces are flat, perpendicular. Some have a slight angle for low reflectance. Some have great angles to manipulate the light. So any type of system should provide the ability to change and vary that angle dependent, for your development needs. And sometimes it gets a little complex, even, so you can have multiple facets on one edge for certain reasons. And also, most of the time, you're polishing multiple edges of the same chip. So all these needs should be provided in the fixturing that you're using. When you're mounting a chip in the polishing fixture, you're kind of at the mercy of the machining tolerances as how it's held perpendicular to the polishing surface. Another approach is to actively align the chip in the fixture. In this sample here, we're using a optical connector of a known geometry, and we hold it over an interferometric device. And there's a gimbaling mechanism which you can adjust to change the planarity of the fixture itself in reference to the polishing surface. And by monitoring a fringe pattern, you can dial in that geometry. So basically what you're doing is you're aligning at the point of contact of polishing. And what that does is it negates any of the machining tolerances and assembly tolerances throughout the machine. You're aligning right where you're going to be polishing. Another important feature is to have some type of independent suspension. This is a freedom of z-axis movement with some type of linear slide mechanism, and this gives you a better control over pressure against the film, and it also guarantees constant pressure throughout the polishing process itself. At a minimum, any polishing machine should give you the ability to control the three major polishing variables, which is pressure against the film, polishing rotational speed, and cycle timing for each of the steps. Ideally, you should be able to control all these features in real time and adjust them actually while you're doing the polishing. Basically, this type of a manual mode and adjustment gives you the data and information that you would need to later create polishing programs. So you go from the manual type mode where you can adjust everything on the fly, and then you can take that data and create actual polishing programs that can use the processing on a more consistent basis. And motion control is important, especially with delicate type waveguides. As opposed to just coming down into contact with the polishing film, if you have a feature where you can incrementally slowly advance the component to the polishing surface at a slow programmable rate, that avoids and minimizes any chance of damage of the component. Also, for larger surface areas, you're always trying to balance material removal with the polishing pressure, and a feature like this helps you achieve that. We found with many type of projects we're on, material removal of the edges is important and critical, and sometimes it has to be maintained on levels of, on the average, plus or minus 25, 30 microns. In order to achieve that precise material removal, any motion control in the system has to be moving on a better level than that. So you're looking for a system that can position the chips 10, maybe 5 microns, and this will give you the amount of material that will be removed. And one thing you learn when you start doing polishing, polishing is more of an art than a science. There are many types of waveguide materials out there: silica, silicon carbide, sapphire, glass, and there's many types of polishing abrasives: diamond films, silicon carbide, aluminum oxide. So you're always, the process development is kind of a trial and error basis that takes time. And just be prepared when you purchase a system, you're going to have to put some effort in developing the actual processes themselves. And preferably, you're not performing the polishing blind. If you have some type of video integration into the equipment, it helps monitor the process. In many cases, we see chips that actually have laser etched marks on it, which are kind of like, don't polish beyond this point marks. And the only way to actually use that is to actually view the chip as it's polishing. Once you determine again, you can put that into a program, and the video monitoring may not be necessary at that point. And in addition to monitoring with a video scope, if you have a feature that you can do the inspection of the surface image while the chip is still loaded in the fixture, basically you're doing your QA in the machine. If any touch-up processes are necessary, the chip's loaded, and you want to avoid loading and unloading a chip as much as possible. So if you have some type of way to place a video scope underneath and then do the inspection right in, it reduces material handling and potential damage, transferring to independent stations, and contamination at the same time. And while you have the chip in, you might as well make measurements on it. Measure your angles, measure your material stock removals. Again, everything accomplished with the chip not being removed from the machine itself. Okay. So, when you're in the R&D phase, you want that flexibility. You know, changing angles, adjustable clamping mechanisms. The only problem with that is it takes up space, those mechanisms to accomplish that. However, once a chip design has been solidified, you know the dimensions, you know the angle it's going to be, what you can do is make individual carriers specific to that chip itself. This way, it's a smaller footprint of the device. Then these beaks can be loaded offline, and then you can populate them in a multi-position fixture. And then basically you're polishing groups of waveguides at the same time, all identical to each other. And to further increase throughput, what you can do is when one group is polishing, you can have offline loading stations and basically reference all your chips and basically swap out one fixture with another fixture and just continue on, again, to get maximum throughput for production. We touched on independent suspension a little earlier, but it's actually more critical when you're polishing multiple waveguides. Here, each position has its own independent suspension. So one location is not getting any excessive more pressure than its adjacent position. This gives you a much more uniform pressure distribution when you make contact with the film, and it also guarantees that all the components will be in contact during the entire polishing process itself. And ideally, if you do optical alignment, again, where you do the collinearity of each of those positions, then you accurately align each one to the polishing surface itself. And then, of course, in production, you can't have manual modes. You pretty much need to have a program, so you have simple prompts for technician to technician, pretty much summarizing what the process will be and telling them what steps to do, changing films, changing polishing pads. We've been talking about, this presentation has been waveguide centric for the most part, but you know, you also have to get light into the waveguide and light out of the waveguide and coupling basically. So there's other interconnect components such as fiber arrays, chips, multi-fiber connectors, V-grooves, shaped fibers, lens fibers. If you're specifying a polishing system for waveguides, if it can also support other components such as these, you'll get the maximum of your purchase also. Quick little sales pitch. We at Krell developed our Nova system. We call it a work cell approach because it integrates what we're talking about, polishing and inspection, into one workstation. Basically, your technician is also your QA manager in a certain way. It's modular and configurable, hence you can set it up for R&D fixtures, go to production levels, and also, as I just discussed, the interconnect photonic components also. We use a familiar Android interface that everyone is easy to program and easy to operate. And we address all the PIC challenges, basically stock removal, angle, and surface finish. So we're here at the show. If anyone is interested, please stop by our booth. We have a staff of engineers that can answer all your technical questions. And speaking of questions, Anybody have a question?
Oh, okay. So I imagine that you're the last person to touch the FAU or the PIC before someone gets to optically tested. And that's an awkward position to be in because as a big optics guy, you're on strategy, as a wave optics guy, you're on optics guy. How do you manage that kind of risk? Do you ever get involved in having to test those modes, and how do you wind up specifying how much polishing is appropriate to give people a mode profile that they want?
Well, a lot of times, most of the process development is kind of on the responsibility of the users. I mean, they're familiar with the chips. We usually provide base programs, suggested films, surfaces, pressure, speed, but it's a baseline. It works, but it can be optimized. We may use expensive diamond films, but they work great, and we provide you that setup. But you can take it to another level and say, hey, maybe silicon carbide, which is like a tenth of the cost, especially in production, will work just as well. But you kind of have to do that yourself.
Yeah, thank you. There's several presentations yesterday by Corning. Actually, they prepared their waveguide edge by lasers. Just one shot of laser and get a very good surface and can do the fiber coupling. So how do you compare this to? If laser can get, number one, is very quick. Number two, is manufacturable. This more of a, in my opinion, is a research tool because it's probably spend much time to get one chip ready. So can you get comparison about the Corning's approach and your approach?
Well, I'm not familiar with Corning's approach, but I am. We've been in business for 30 years, and initially it was fiber optic connectors for telecom, datacom, and that was always polishing too. But in the past 15 years, people have laser type, call it processing to get the surface finish. However, they're still polishing 15 years later. So even though Corning may have this method, I haven't seen it, be interested in seeing it, but
So the market for your system, it's expanding or shrinking?
Oh, it's expanding.
Expanding.
I mean, 75% of our inquiries for polishing equipment is all waveguide and PIC related. And, 5 V-groups and that type of thing, that interface.
I had a question on polishing the facet.
Yeah.
You showed very nice polishing at angles, but
Yeah.
are you able to polish concave or convex kind of shapes?
We've never been asked. Just going back to connectorized fiber, or ferro, terminated ferrules, there are ways of putting not concave, but convex surfaces. Actually, that's what you want to do when polishing fiber optic connectors. And that's determined by the polishing surface you're using. If you use rubber, softer backings with a film on top, you will put radiuses on the edges. We found most people want them flat, but if you go against, and therefore we use glass substrates for polishing, to get that flat finish. If you use a soft durometer, a 40 durometer rubber pad, that would put a radius on the edge. To what size, radius, I don't know. That's again something going back to, you gotta try it and measure it yourself. Because it's not just the rubber you're using, the durometer, it's also the amount of pressure you're using and the type of abrasive you're using. There are polishing films called flock films that are like fibers of a felt, and the abrasive is built into the fibers themselves. So when you polish, it does put a radiusing effect. Because it's like putting it into a carpet, with abrasive. So when you're polishing it, it kind of moves the edges. Again, experimentation though.
Last question.
Can you comment on dry versus wet polishing?
Yes, everyone asks that question. And our answer usually is, if you can do it dry, it's a cleaner process. If it passes your optical specifications for attenuation or transmission. However, using a wet polish, and when I say wet, it's just like sprays of water, it's not a continuous flow, it does give you a better surface finish using wet. And there are some polishing films, like silicon dioxide films, to activate them, you have to have them a little bit wet too. So the whole thing, usually a process with PICs and connectors, it's a multi-step process. So the first few steps can be dry, but the last step or two, you can use wet just to get a better surface finish. And one other thing is, we're grinding basically. So it creates debris. If you do the steps wet, that does help contain the polishing abrasive of the component itself and also the polishing film.
Maybe we could take it offline. I think we are out of time, so I just
Just a quick question. What is the minimum surface roughness you can obtain?
Surface roughness is on the order of RA of like 5 nanometers.
Okay.
Yeah. And again, that's determined by the last step, and that would be kind of the best for the that we've seen at least.
Thank you.
thank you. Let's thank our speaker and also conclude this session.